Today we're going to look at an interesting problem involving counting the number of ways that a natural number can be expressed as the sum of two squared integers. And we're going to call that number of ways r sub 2 of n. And what we'll end up proving is that r sub 2 of n is equal to 4 times the sum over all odd divisors of n of -1 to the d minus 1 over 2, where d is one of those odd divisors. Now, before we jump into our method here, which will involve generating functions, and maybe this isn't the easiest method, but I think it's a method that highlights a lot of nice techniques, let's look at some examples. And so just to be clear here, this r sub 2 of n is counting the number of solutions to n equals x squared plus y squared, where x and y are integers. That means that we get a bunch of seemingly extra solutions by swapping the roles of x and y and looking at positive and negative values for x and y. So let's observe that r sub 2 of 0 is 1. And that's because 0 is 0 squared plus 0 squared. But over here it looked like this number needed to be a multiple of 4. But let's backtrack a little bit and notice that this only holds for n bigger than or equal to 1, so we're okay. Now r sub 2 of 1 is equal to 4. Let's observe that 1 is equal to plus minus 1 squared plus minus 1 squared. We get 2 choices here times 2 choices here is 4 choices altogether. But we can check that this works with our formula. 4 is equal to 4 times 1, or minus 1, to the 1 minus 1 over 2. We only have a single odd divisor, and that's the number 1. Now r sub 2 of 25 is 12, and we can enumerate those pretty easily. We've got plus minus 5 squared plus 0 squared. That's 2. 0 squared plus minus 5 squared, so that's going to be 2 plus 2 is 4 total so far. And then we have plus minus 3 squared plus minus 4 squared. That gives us 4 more. And then we get 4 more from the symmetric version of that one. All in total we have 12. 4 plus 4 plus 2 plus 2. But let's observe that our formula holds as well. The odd divisors of 25 are kind of obviously going to be 1, 5, and 25. And let's observe that 12 is equal to 4 times 3, but we can write 3 as 1 plus 1 plus 1, or minus 1 to the 1 minus 1 over 2, minus 1 to the 5 minus 1 over 2, and minus 1 to the 25 minus 1 over 2. Now, it's not always possible to write an integer as a sum of squares. I have an old video on exactly when this is possible if you want to check that out. But let's observe that r sub 2 of 7 is 0. It's impossible to write 7 as the sum of two squares. And we can just by hand check that by looking at sums of squares of numbers. Let's see, it's got to be less than the square root of 7. Or I guess less than or equal to the square root of 7. But we can go a little bit higher if you want to, just to be sure. So notice that 7 is bigger than 0 squared plus 2 squared. But it's less than 0 squared plus 3 squared. So that means 0 squared plus something squared won't work, but that's obvious because 7 is not a perfect square. 7 is bigger than 1 squared plus 2 squared, but it's less than 1 squared plus 3 squared. So 1 squared plus something squared won't work. And then 7 is less than 2 squared plus 2 squared. So 2 squared plus something won't work. Now, let's observe that also, plugging into our formula over here, which we're going to prove, we also get 0. 0 is 4 times 1 minus 1, or negative 1 to the 1 minus 1 over 2, plus negative 1 to the 7 minus 1 over 2. Notice 7 minus 1 over 2 is 3, so we get negative 1 to the third power, which is pretty clearly still negative 1. Okay, cool. So now that we've got some examples, let's maybe start our proof of this nice result. Okay, so we're going to use a pretty technical result for our proof, but I've proved this on the channel before if you want to check it out. It's called the Jacobi triple product identity. It says that the product as m goes from 1 to infinity of 1 minus q to the 2m times 1 plus q to the 2m minus 1 times z times 1 plus q to the 2m minus 1 times z to the minus 1 is equal to this sum as n goes from 0 to infinity of q to the n squared times z. So let's observe that if we set z equal to 1, we get the sum as n goes from 0 to infinity of q to the n squared. And I just observed here that this is a mistake. This should have been from minus infinity to infinity. Now, I'd like to point out that that looks kind of like what we would call a souped up version of a geometric series. Notice the sum of q to the n would be a geometric series, but here we've got an n squared here. That's actually called a hypergeometric series. And if we, like I said, set z equal to 1, this product identity gives us the simplest closed product form of one of these hypergeometric series. Okay, so anyway, let's get into the proof. So I'm going to sketch out our first step. So let's look at the sum as n goes from 0 to infinity of r sub 2 of n times q to the n. Like I said before, we're going to use generating functions. So if we can get some nice form of this series and extract the coefficients, then we can prove this identity. So let's observe that this is going to be 1, so that's going to be the number of ways to write 0 as a sum of two squares. And then we'll have plus, and now I'm going to write this as follows. This is going to be q to the 1 squared plus 0 squared plus q to the minus 1 squared plus 0 squared plus q to the 0 squared plus 1 squared plus q to the 0 squared plus minus 1 squared. And I'm doing that in particular, I'm taking this term right here, which is 4 times q to the first power, and expanding it like this because I'm going to perform a factorization. And once you've seen factorizations like this is like an obvious factorization, but before you've seen it, it's a little bit gnarly to look at. So I'd like to factor this as follows. So I'm going to factor this into two sums, which I'll eventually pack together into summation notation. But for now, I'm just going to write like this. So I'm going to put 1 in the middle, and then I'm going to put plus q to the 1 here. I guess I should say q to the 1 squared, and then q to the minus 1 squared back this way. And then, of course, that's going to go infinitely in both directions. Then here I'm going to have q to the minus 1 squared here, and q to the 1 squared here. And now let's observe if I take this 1 here and multiply it into this q to the 1 squared, I'm getting this term, this q to the 0 squared plus 1 squared. But then if I take, let's say, this q to the minus 1 squared, and multiply it into this number 1 here, I get q to the minus 1 plus 0 squared. And as you can see, by using the distributive rule for the rest of those terms, like for example, this one right here up to this number 1, which would correspond to this term, and then finally this number 1 here, and this q to the minus 1 squared, which would correspond to this term, we're able to capture where all of our q to the first power terms came from. And now you can expand this out, and what you'll see is that this is the way to capture all of the ways to write n as a sum of squares. And in fact, we can package both of these together into perhaps the sum as m goes from minus infinity to infinity of q to the m squared times the sum as n goes from minus infinity to infinity of q to the n squared. So this m index thing would be this first term, and the n index thing would be the second term. Or if we want to be a little bit more succinct, we could write this as the sum as n goes over all integers of q to the n squared, and then we'll square this. Okay, so that's an important enough realization to write at the top before we jump into our main arguments. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing. It really helps out. Okay, so we just argued that our generating function for the number of ways to write n as the sum of two squares can be written as the square of this fairly simple hypergeometric series. And now we're ready to start with our argument involving the first round of application of the Jacobi triple product. So I'd like to start with this term right here, this z minus z to the minus 1, multiplied into this infinite product. So notice it's a product over m, and we've got 1 minus q to the m, 1 minus q to the m times z squared, and 1 minus q to the m times z to the minus 2. Now, I'd like to observe that I can multiply this object through and maybe stack all of the terms with this z to the minus 2 thing, and then do a little bit of re-indexing and end up with the following. So this is going to be equal to z times the product as m goes from 1 up to infinity of 1 minus q to the m, and then we're going to have 1 minus q to the m times z squared, and then we'll have 1 minus q to the m minus 1 times q to the minus 2, times z to the minus 2. And now just to sketch out how that's going, let's observe that this z times z to the minus 1 can be written as z times the quantity, 1 minus z to the minus 2. Now what we're doing is leaving this z out front, and we're taking this 1 minus z to the minus 2, and then we're going to include it with these terms over here. And so now notice the terms over here that are attached to z to the minus 2, before multiplying this on, start with a power of q, which is q to the first. But after multiplying this term on, they start with a power of q, which is q to the 0. So we can encode that into our big product by changing this q to the m to q to the m minus 1. So we re-indexed it to absorb this 1 minus z squared. Okay, cool. So now what we can do is apply the Jacobi triple product identity, and that's what we're doing in this step. So I'll just say we're using the Jacobi triple product identity, and it's going to be with the following substitutions. So q is going to be replaced with q to the half. That's pretty clear because we've got a q to the m here, whereas in the Jacobi triple product identity we have q to the 2m. And then z is going to be replaced with minus z times q to the half. I should say minus z squared times q to the half. That's pretty clear because let's observe that we're getting z squared here and a z to the minus 2 there. That's where this z squared comes in. And then this q to the half is going to gobble up this q to the 2m minus 1 type terms. Okay, cool. So let's put a little box around that so that we can just hold it to the side. That's the substitution that we just made. And that's going to allow us to write this as z times the sum as n goes from minus infinity up to infinity of minus 1 to the n times q to the n times n plus 1 all over 2 times z to the 2n. So notice we get a q to the n squared over 2 from this replacement right here. And then we get the plus 1 over 2, or the n over 2, from this substitution right here. So in the end, we have q to the n times n plus 1 over 2 for our power of q there. But next up, what I'll do is I'll take this z and I'll insert it into the sum by putting a 2n plus 1 there. And then I'm going to take this and split it into the odd terms in the sum. So here I'll just say n odd plus the even terms in the sum. So I'll say n even. And then we're going to have the same sum and minus 1 to the n, q to the n times n plus 1 by 2, and then z to the 2n plus 1. But now what we can do is use the fact that when n is odd, this -1 is going to be a -1, then -1 to the n. And when n is even, that's going to be a +1. And this is after re-indexing to take into account that we've got just even terms and odd terms. So maybe just to sketch that here, this would be replacing the n's with, let's see, maybe 2 times n minus 1. And here it's replacing all the n's with 2n. Okay, cool. So that's going to leave us with the sum over all integers n of, so we're going to put the positive ones first, so that'll be replacing n with 2n. So we'll have q to the n times 2n plus 1, and then z to the 4n plus 1. So that would be this even part of the sum, and then minus the odd part of the sum. So that's going to be the sum as n goes over all integers of, so now this is going to be q to the n times 2n minus 1. We're replacing n with 2n minus 1. And then z to the 4n minus 1. Okay, so now let's bring this expression up, and then we're going to use another round of the Jacobi triple product identity. So if you like the kind of combinatorial number theory that we're doing in this video, I made a whole course on number theory that ends with maybe 6 videos about combinatorial number theory or Ramanujan style of number theory on my second channel, Math Major. And in fact, that channel is kept ad-free due to my support from channel members and patrons. So if you'd like to help me keep that ad-free, think about joining the Patreon or becoming a channel member. But now back to this proof. So this is where we ended up. And now what we're going to do is use the Jacobi triple product one more time. Maybe not one more time for the whole proof, but one more time at the moment. So I'll just say here we're using the Jacobi triple product identity, where q is now being replaced with q squared instead of q to the half. And then z is being replaced with z to the 4th. And then q to the plus minus 1, depending on if we're in these, what were originally the even terms or the odd terms. Okay, cool. So now let's see what the Jacobi triple product identity with that will give us. So let's see, for the first one we'll have a z, so that's factoring this z to the plus 1 out and leaving the z to the 4n in there, because that's really what we need this to look like here. That should have been an n from before. And that's going to give us z, and then the product as m goes from 1 to infinity of 1 minus q to the 4m, and then we'll have 1 plus q to the 4m minus 1 times z to the 4, and then 1 plus q to the 4m minus 3, and then z to the minus 4. Okay, so that's from this first term with this Jacobi triple product identity. And for the second term with the Jacobi triple product identity, we'll have minus z to the minus 1, and then we'll have the product as m goes from 1 up to infinity of another 1 minus q to the 4m. And now we're going to have 1 plus q to the 4m minus 3 attached to z to the 4, and 1 plus q to the 4m minus 1 attached to z to the minus 4. So notice these two products look really, really similar, except this kind of switch in the roles of 4m minus 1 and 4m minus 3 type terms. Okay, so this is important enough from this first line to this last line to start a whole new board with that, so let's do that. Okay, so now here's where we ended up. We had this product over here on the left-hand side was equal to the difference of these two products on the right-hand side. Now I'm going to use shorthand for these, which I'll define over here. We'll think of L as being the left-hand side, and then R1 is the first term on the right-hand side, and R2 is the second term on the right-hand side. And now what we're going to do is take the derivative of both sides of this with respect to z and then set z equal to 1. So let's look at dl by dz evaluated at z equals 1 first. So that would be the left-hand side. So we're going to use the product rule for this. So let's maybe take the derivative of this second big product first. So maybe I'll use the notation that this thing that I'm overlining in blue is just blue box. So that means I'm going to have z times z inverse times the derivative with respect to z of blue box. And then I need to evaluate this at z equals 1. But now let's observe that if I evaluate this at z equals 1, this becomes 0 because of this z minus z to the minus 1 term. That means we don't even need to worry about taking the derivative of blue box with respect to z because the term it's attached to goes to 0. That means all we have to do is take blue box times the derivative of this z minus z inverse. So the derivative of z minus z inverse is going to be 1 plus z to the minus 2 times this big product. So now this is going to be the product as m goes from 1 to infinity of 1 minus q to the m. And now I'll just go ahead and set z equal to 1 here. So we're going to have, let's see, another 1 minus q to the m and another 1 minus q to the m. So in the end, it's going to be 1 minus q to the m cubed. And then when we set z equal to 1 here, let's observe that this just simply gives us the number 2. So that means that after taking the derivative of the left-hand side with respect to z, setting z equal to 1, we get twice. And then this product as m goes from 1 to infinity of 1 minus q to the m all cubed. So let's maybe put that up here just for safekeeping. So the derivative of L with respect to z, setting z equal to 1 is 2. And then the product as m goes from 1 to infinity of 1 minus q to the m cubed. And now that we've got that for safekeeping, let's go ahead and take the derivative of one of the terms on the right-hand side. We'll take the derivative of R1, and R2 will have a similar maybe structure. All right, so now to take the derivative of R1, we're going to use a trick from Calculus 1 class, and that is logarithmic differentiation. So let's observe that the natural log of R1 is going to be the log of z. And then after that, we're going to have the sum as m goes from 1 up to infinity of the log of 1 minus q to the 4m plus the log of 1 plus q to the 4m minus 1 times z to the 4 plus the log of 1 plus q to the 4m minus 3 times z to the minus 4. Okay, nice. But now if we take the derivative of both sides with respect to z, let's observe that in the numerator we'll have r1 prime. So I'll just write r1 prime for the derivative of r1 with respect to z just to keep it simple. And then in the denominator we'll have r1. And then while we're at it, let's set z equal to 1 just to save time. Okay, so now taking the derivative of natural log with respect to z will give us 1 over z, set it equal to 1, we'll just get the number 1. Then, well, let's see the rest of these terms. So we're going to have the sum as m goes from 1 to infinity. The derivative of the first term with respect to z is 0 because there's no z in here. And then for the next term, we'll have 4 times q to the 4m minus 1 times z cubed. But we're setting z equal to 1, so I'll just append the z cubed. This is going to be over 1 plus q to the 4m minus 1. And then for this next one, we'll have minus 4 q to the 4m minus 3 times z to the minus 5, I guess. But we're evaluating that as equal to 1, so that goes away. And then we'll have 1 plus q to the 4m minus 3 down here. But now what we can do is just multiply both sides by this r1, and we've got a formula for r1 prime. So let's notice that r1 prime is going to be equal to r1, which is this big product right here that includes the z, and then times 1 plus our sum as m goes from 1 to infinity of 4, which I guess I can factor out of the whole thing. And then we've got q to the 4m minus 1 over 1 plus q to the 4m minus 1 minus q to the 4m minus 3 over 1 plus q to the 4m minus 3. Okay, nice. And now you can do something very, very similar for R2, so I'll leave that to you. And then we'll jump to the result of having taken the derivative of this entire equation with respect to z and setting z equal to 1 and see what we have. Putting together all of the differentiation on both sides of that equation from the last board, we ended up with the following identity. So we've got 2 and then this infinite product of 1 minus q to the m cubed, and then this big thing on the right-hand side, which I won't read out. Now, I'd like to observe the following kind of related object, which will help us simplify this a little bit. Let's observe if we take the product as m goes from 1 to infinity of 1 plus q to the m all squared, and then 1 minus q to the m. We can take one of these 1 plus q to the m's and pair it with the 1 minus q to the m and write it as 1 minus q to the 2m. So we can write that as the product of, like I said, it's going to be 1 plus q to the m and then 1 minus q to the 2m. Okay, nice. Then after that, we can take this 1 plus q to the m and split it into even and odd parts. So that's going to give us this product as m goes from 1 to infinity of 1 plus q to the 2m, and then 1 plus q to the 2m minus 1, and then we've got this 1 minus q to the 2m still floating around there. But then we can take this 1 plus q to the 2m and this 1 minus q to the 2m and multiply them together, and simultaneously take this 1 plus q to the 2m minus 1 and split it into both odd types, if you will. So that will be 1 attached to 4m minus 1 and 1 attached to 4m minus 3. So that'll give us the product as m goes from 1 to infinity, 1 minus q, or 1 plus q to the 4m minus 1, 1 plus q to the 4m minus 3, and then 1 minus q to the 4m from those two terms multiplying together. But now what I'd like to observe is that we have just achieved this term right here that's on the right-hand side. So what we'll do is we'll divide the left and right-hand side of this equation by the left and right-hand side of this new equation that we have just built. So let's observe on the right-hand side, it's simply going to cancel all of this out. Then on the left-hand side, this is going to get canceled down to a 2 and then give us a 1 plus q to the m squared in the denominator. And then finally, we can cancel these 2's out as well. Okay, so let's start the next board with that canceled out equation. Okay, so here's the result of that last calculation. Now we're going to make another accessory calculation, if you will, before we finish it all off. Let's start with the sum as n goes from minus infinity to infinity of minus q to the power n squared. Now I can use the Jacobi triple product identity on this. Maybe as a bit of an exercise, I'll leave it to you to decide what the exchanges are, the substitutions are for the Jacobi triple product identity here. But what we'll have is 1 minus q to the 2m minus 1 all squared, and then 1 minus q to the 2m when all is said and done. But now what I can do is take one of these 1 minus q to the 2m minus 1s and pair them with the 1 minus q to the 2m, and that's going to achieve 1 minus q to every power. We get the even ones here and we've got the odd ones here. That leaves us with another copy of 1 minus q to the odd though. So that allows us to rewrite this as the product as m goes from 1 to infinity, 1 minus q to the 2m minus 1, and then 1 minus q to the m. Okay, cool. And now I'm going to do a little step which I'll leave as a bit of an exercise, and this is related to Euler's proof that the number of partitions of n into odd parts is equal to the number of partitions of n into distinct parts. This allows us to write this as the product as m goes from 1 to infinity of 1 minus q to the m over 1 plus q to the m. Okay, so now let's save this identity maybe over there in the corner, and we're ready for the last steps. Okay, we're finally ready to finish this thing off. So let's start with our generating function for the number of ways to write n as the sum of two squares, which before we noticed was the square of this hypergeometric series. but I'm going to rewrite this as the hypergeometric series minus q to the n squared, and then where q is replaced with minus q. So that's just replacing q with minus q twice up there. But now we can use our pink boxed result from the last chalkboard, and that allows us to write all of this as all of this squared with the replacement of q with minus q. But all of that right-hand side squared is equal to all of this. So I can just really replace it with this line right here, this 1 minus 4 times the sum of all that, where q is replaced with minus q. So that's going to leave us with 1 plus 4, and then we'll have the sum as n goes from 1 to infinity of q to the 4n minus 3 over 1 minus q to the 4n minus 3 minus q to the 4n minus 1 over 1 minus q to the 4n minus 1. Now we're pretty much home free. We can expand each of these as geometric series, and we'll see that this now looks like 1 plus 4, and then we'll have maybe an outer sum which will be indexed by n, so n goes from 1 to infinity, and then the inner sum will 1 to infinity of q to the 4n minus 3 times m minus q to the 4n minus 1 times m. So again, that's geometric series there where our common ratio is, well, q to the 4n minus 3 in one of them and 4n minus 1 in the other one. But now let's observe that we can take this sum and rewrite it in this clever way. This is going to be the sum as n goes from 1 to infinity of what? So this is going to be the sum over all the divisors of n, where these divisors are congruent to 1 mod 4 of the number 1, minus the sum over all of the divisors of n, where that divisor is congruent to 3 mod 4 of 1. And that's all multiplied into q to the 1. And just to be thorough here, what's going on here is we're re-indexing this so that all of this right here is our number n, and our divisors are chunking through these things that are of the form 4k minus 3, if you will, which are congruent to 1 mod 4. And the same thing over here, we're chunking all this together so that this is our number n, and then our divisors that we're running over are these 4k minus 1 ones, but those are congruent to 3 mod 4. So there's a bit of re-indexing that goes on right there. But now let's observe that if we take this left-hand side of the equation and then this right-hand side of the equation here, and then extract the coefficient of q to the n, we get exactly our result. That's given, of course, that if the divisor is congruent to 1 mod 4, this is equivalent to minus 1 to the d minus 2. And if our divisor is congruent to 3 mod 4, that's also equivalent to minus 1 to the d minus 1 over 2. And that's a good place to stop.